We're going to get started here on today's webinar. So my name is Mackenzie Woodman, and today we'll have a guest speaker, Pooja Sheevam. So today we're going to be talking about infrared spectroscopy and applications for geothermal exploration and reservoir characterization. So first I'll go through a little bit about who spectral evolution is, and then I'll let Pooja take it away with her presentation. We can do next slide. So Spectral Evolution is the leading manufacturer of UV-Vis NIR, 350 nanometers to 2500 nanometers, field-based spectrometers, and spectroradiometers. We've been around since 2004, so about 21 years. And we're located in the Boston area in Haverhill, Massachusetts. So we can do next slide. So our primary applications are in hyperspectral applications, remote sensing and vegetation, as well as mining and geology research, which is what we'll be focusing on today, and photonics and calibration transfer. So like I said, today's guest speaker is Pooja Sheevam. Pooja is an early career geologist who recently got her PhD in geology at the University of Nevada, Reno, at the McKay School of Mines, specializing in the application of infrared spectroscopy for geologic exploration, especially in mineral and ore deposits. Her dissertation focused on applications in infrared spectroscopy for characterizing hydrothermal mineralization in Hawaii and geothermal exploration. And her expertise ranges from hyper and multispectral remote sensing image analysis, in situ field spectroscopy, and laboratory and high resolution spectroscopy. Pooja is currently employed at the New Mexico Bureau of Geology and Mineral Resources, the New Mexico State Geological Survey, and us at Spectral Evolution are very grateful to have her sharing her expertise with us and her experience with spectrometers and spectroradiometers. So thank you very much, Pooja, for being here, and I'll let you take it away from here.
Awesome, thank you. Audio coming in good?
Sound great.
Perfect. Awesome. Well, I just want to thank everyone for taking the time of their day to talk about something I look forward to talking about infrared spectroscopy and its applications in the renewable industry, specifically geothermal. Geothermal is not new, but it's becoming newly relevant, and how we characterize these systems, especially in the geology and exploration phases, are going to become more and more relevant. So not to go too much into my already said bio, but as mentioned earlier, I just received my PhD in geology at the University of Nevada, Reno. My dissertation really focused on infrared spectroscopy techniques. I went from a bird's eye view logging tools to really ultra high resolution, down to about 50 micron micro FTR scanning instruments. I have used everywhere from visible to long wave infrared, up to about 20 microns. And the spectral evolutions instruments were actually really key in my dissertation in the research sense, because it was sort of the first infrared instruments we used, and that kind of dictated and set up the rest of my research. The one at UNR, I don't know if you can see my mouse or if a pointer will work better. But the one at UNR is the Spectral Evolution RS5400. I am since then have moved to New Mexico, where I've taken a position through the Geological Survey. It's the energy division, and this essentially is the science and research division of the State Natural Resource Office. And we do have an ore express instrument. The only problem is the Bureau for the longest time didn't have a spectral geologist, so they didn't really know how to use it, but now I'm here. And I hope to kind of expand the scope of research. Right now we're applied for a critical minerals grant and funding opportunity. And currently we also have a huge repository of core and cuttings, and I hope to sort of expand the data associated with those core and cuttings here at NM. So to start off this presentation, I'm just going to assume that there are folks that may not know fully the capabilities of infrared spectroscopy, or maybe need a refresher. Spectroscopy is a non-destructive analytical tool that, when used properly, can be a quick way to identify materials. That's also very much supported in the literature. Here, I actually created my own word cloud based on the abstracts, highlights, and introductions of some of the top cited research papers that use spectroscopy in geology. And again, you can see a lot of the language that's used, right? Cost effective, rapid, sensitive. But these are some common features of spectroscopy and why we use it. So I begin with the fundamentals and remind us, what the properties of light are. Basically, when light waves or photons interact with matter, whether it's a gas, solid, or liquid, light can be reflected off. It could be scattered or refracted based on the material that it's hitting and the thickness. And finally, it can be absorbed into the electron structure, which I kind of identified here, small schematic here, but absorbed into the electrons surrounding the molecule or the atom. And when those electrons become excited, they go to different energy levels within the valence structure. This is what we exploit when we talk about spectroscopy. So in geologic exploration, infrared spectroscopy largely deals with, how this light interacts with that structure. And that data is usually between visible to long wave infrared. For this presentation, I'm really just going to be focusing on the short to long wave infrared. So the shortwave infrared is widely used in geological exploration, especially when determining aqueous environments. That's because the wavelength range is great at detecting aqueous secondary minerals. So those minerals are essentially indicate the presence of water or past presence of water as the medium or as the method to alter what is essentially the parent rock or the original rock to something different like a clay. So this chart just shows where do you expect absorption bands. So for example, the presence of an absorption band around the 1900 nanometer feature indicates that there's just a water molecule in the sample. The same with hydroxyl kind of ranges. So we tend to focus on the 2 to 2.5 micron because that's tends to be where the diagnostic features are in geology. And here I'm not talking about wet rocks or wet sample, rather that hydroxyl carbonate, water, or within the molecular structure, within the crystal structure. So in geology, we tend to use the term hydrated, right, in the literature. And what that looks like is something like this. Here I provide some examples of pure mineral spectra. So these are determined to be like the end member of that specific mineral group through other methods. And this is from the United States Geological Survey library that's publicly available. And so here, an example of alunite, the diagnostic absorption features associated with hydroxyl give you what I would say called bunny ears. You have other ones in the longer wavelengths. Many smectite group minerals have diagnostic features between, again, that 2 and 2.5 area. And these are just examples, right? With a trained eye or even access to mineral libraries where you can match the collected spectra or data that you have, you can quickly speciate minerals in your sample. And I'm not talking, oh, this is just a sulfate, but you can get the specific end member of that sulfate mineral. The same principle applies to longwave. Now here's a sketch from an older publication. Not much has changed though in terms of how we understand this. And the longwave, we tend to focus on what we call the silica bonds. And there are some influence of hydroxyl and carbonate and sulfate, but it's important to understand that the longwave really interacts with those silica bonds and causes a lot of those absorption and crescents and peaks that we see. And so an example of something that looks like that, here I have feldspar, and then I have olivine group. Longwave can get a little bit more complex, as I found in my own research. even the slightest mineral substitution can cause absorption shifts and variations. As you can see in the feldspar group, just going from potassium, sodium to calcium, you get variations of what basically kind of looks like the similar absorption features between 8 and 10 microns. Here, olivine's a little bit more simpler, right? It's just iron, magnesium bonded to the silica SiO bond. And here you can see as we go from the forsterite to thiolite and member, you get shifts in absorption, even though they're the same shape, into the longer wavelengths. We find the iron absorption into the longer wavelengths is also something that's seen as a trend in the shortwave, just to briefly bring up. But very subtle things can cause shifts and transitions for the long wave. Now, this can all be overwhelming if this is something that you're new to or you're still trying to learn and grasp. But luckily, we have a cheat sheet. So if you're a geologist or a company wanting to implement spectroscopy or into your research, I think having a strategy based on realistic outcomes is very important. So TerraCore came up with this really awesome cheat sheet that sort of tells you what you can best detect in each wavelength range. In my own experience, in my own research, I find that shortwave is best with these, what we call in geology, secondary minerals, or minerals that are formed after the primary rock has been formed. And that the long wavelength is best for this sort of rock building primary minerals, silicate group minerals. But as you can see, there's crossover, right? They're not simply, it's not end all be all in one wavelength range or the other. The reason I point this out is that sometimes you can get masking or mistake one for the other. And this sort of assessment for long wave and short wave targets is based on confidence rather than the value of data, if that makes sense. So the cool thing about spectroscopy is that it's not limited to a resolution. You can gather data at varying scales and distances. Here I provide things like benchtop instruments that can scan. The scanning ones can do as low as 50 microns. This one takes like a powder or a dust sample. So if you have limited sample, great way to measure it. Right, so this is the spectral evolution, which I use extensively in my research, and you can have it, we just wheeled it around and logged core, or you can take it out in the field. Scanning instruments, great for larger samples or if you have a lot of sample. And then, of course, remote sensing, great for covering large swaths of land, especially for preliminary research. And of course, spectroscopy is not new, like I said earlier. In fact, it's widely used in other industries. I think I recall a conversation with SpecIn. One of their reps actually mentioned that food services and like the food industry and food science is like their biggest client, which I found very interesting. Agriculture, right, land and soil science, they use spectroscopy like very much in their research and industries. A little bit more closely related to geothermal is the mining industry. Spectroscopy is now being implemented beyond, when I started out in school, this was about 7 years ago. We came in thinking that spectroscopy was only used for the exploration phase to characterize what the resource will be. But now spectroscopy is beyond that. It's used for every stage of mineral exploration and extraction. The reason I bring up mining specifically is because there is crossover between the methods that we use for exploration and mining and for geothermal. And for the most part, it's going to focus on that alteration, right? How is the fluid interacting with that rock? So I mentioned geothermal a lot, but I'm not explaining what it is. So let's get into that. This is a very broad overview of geothermal. Geothermal is an umbrella term that's applied to a variety of temperatures. All in all, in summary, geothermal is in the business and science of heat exchange, whether it's going to be really hot temperatures or much cooler ambient temperatures. We're going to focus on the higher temperature geothermal, which involves a lot more geology and a lot more different exploration methods. Low temperature can kind of be deployed anywhere, really. This high temperature geothermal focuses on electricity generation, which is a huge push if you're in the United States or even in other countries. Is a big push and focus in terms of renewable portfolios. There are some direct use applications, right? We see hydrogen production and maybe for creating cements and aggregates. And, in Nevada, there's a dehydration plant that uses hot fluids. But for the most part, we're going to focus on the electron generation part. So there's also terms, if you do a deep dive in geothermal, things like next-gen geothermal, emerging technologies. Those are all great, but for the purpose of this presentation, I'm just going to focus on the traditional, conventional geothermal, where you have hot water or hot steam through natural geologic phenomena that allows for elevated heat flow. Now, this map I put, over just a simplified map showing the different areas in which conventional hydrothermal geothermal is implemented or has been already developed. And as you can see, there are trends where elevated heat flow is sort of correlated with our plate tectonics and boundaries, or with rifts and structures around the globe. So the types of resources in hot geothermal really depend on the geology. The reason I bring this up, you don't have to memorize the types of turbines, but I'd like to bring this up to give you an idea of what the reservoir is like. So let's say you're drilling and you find hot temperatures, your power plant will be dictated on that geology. So flash steam here is high temperature geothermal fluid, so water dominated. And these fluids that are hot go from a really high pressure system because they're deep underground. They get pumped into low pressure. And so that fluid flashes into vapor, and that vapor is what's going to drive that turbine. So this also kind of relies on some sort of permeability factor, as well as the heat that drives the fluid. Binary down here is more on the lower end. So let's say your reservoir fluid when you drill is not as hot as you want it to be, or the pressure is not as high as you want to be. You could use another fluid that's much lower boiling point, maybe like a refrigerant, or some people are thinking about CO2. Heat that up using this sort of lower temperature, so just slightly above boiling, and then use that to sort of generate the turbine. And then dry steam is that reservoir. Rather than it being water dominated or super hot water, it's actually existing as steam. Well, this is not as common, but it does exist, and we'll go through some examples. Common terms associated if you come across geothermal, there's water-dominated systems or vapor-dominated systems is what you'll hear in the literature. So hopefully now folks can start connecting the dots on how spectroscopy instruments may help aid in exploration. Here's a very, very oversimplified model, but essentially it tells a story on how rocks can be altered based on the system that they exist in. So secondary minerals are great indicators for pH and temperature, as I've demonstrated here, because they have something called stability. So if you study geochemistry, you'll know this. So for example, if you're doing exploration and you detect using whatever method, hopefully spectroscopy, alunite and jarosite, you can quickly determine as a geologist, okay, this is going to be from an acidic system, but it's going to be at a cooler temperature because jarosite stability doesn't really go past boiling point. And so your system probably is not as hot or, was acidic in the past. Now in mining, I know alunite and quartz is very important because not only does that tell you it's an acidic system, but also at a very high temperature, which is super favorable. Same with calcite and quartz combined together. I know in mining, that's also really awesome to see. Again, even though it's not as acidic, it's slightly acidic from dissolved CO2, you still have above boiling temperatures. And as we know, with hot water means a mobility, boiling fluids, and means the mobilization of certain elements and minerals that we like to extract. Next slide. Okay, perfect. And here are just some photos from the field and from cores and stuff of what that kind of looks like, just to get you in that mindset of what are we looking for in the field when we do exploration or when we're drilling, what does it look like, and what we might need spectroscopy as a tool to sort of tease out right here. This looks pretty oxidized, but by looks, you probably wouldn't know that this is, this is a acid sulfate weathering, right? Just by first look. And same goes for here as well. So now that we've kind of covered some of the geological components for what geothermal is, I'd like to get into some case studies in which spectroscopy has been used. And again, I want to just emphasize that infrared spectroscopy is not new, right? But it's becoming newly relevant, especially in the geothermal field. And so the most important outcome for this is to demonstrate that data for alteration minerals and geochemical history is a really great outcome for a lot of the infrared studies that are where they use infrared, for geothermal. Some of my research, I'll demonstrate how it's a great exploration tool when combined with other methods, especially when you have limited subsurface data. And here are the case studies I'm going to be going over. So first is my own research. I'm going to go through this pretty quickly, but essentially we used spectral evolution and other spectroscopy tools to sort of characterize the mineralization of the drill core. I want to highlight two things in this first slide. One is turnaround time, which is around 8 days of roughly 2 kilometers of core, and data output, which now that in geology, there's a big push for not only gathering the most data that you can, but also ensuring that we can do it in a low risk way. So that includes time that's spent, whether the sample is preserved. And we were able, Hawaii has a unique structure, political economic structure where, geologic exploration is very difficult to do. And so we try to implement a method that can maximize that research output. Here there are 3 cores total, 2 on the Big Island of Hawaii and 1 on Lanai Island. So the first 2 on the Big Island, the first one is the PTA, which is the first geothermal well drilled outside the Pune Geothermal Venture, which is near the Kilauea East Rift Zone, which is where the volcano is. So this is in the middle of the island in the Humula Saddle. Here we, again, have limited downhole data. There's some geochemistry, there's a temperature log, there's some resistivity. But here I want to focus on this image cube here. Don't worry about the colors. Simply put, they just indicate where alteration is. Just follow the text here. The alteration, the cool thing that we found is that the alteration followed this temperature gradient, and it also agreed with this resistivity data. And so here we see in the blue, it's really low resistivity, likely indicating a geothermal fluid further down. And then here again, agreeing with that temperature, it reached above 140 degrees Celsius, so well above boiling. And as we get to the bottom, we start seeing quartz mineralization, even though we see indicators of higher temperatures. Here, it really just tells us, hey, if you drill further or you are wanting to go further, you're going to hit hotter fluids. And there's a likelihood that this well is very promising. Now, the second one is the KMA, which is actually right next to the PTA. It was kind of targeting this western flank of that resistivity indicator. Oh, wrong slide. The odd thing about this KMA well was the temperature did not mimic what they were expecting in the PTA, but the alteration was also very different. What we found was a lot of acid sulfate minerals between jarosite and alunite and some opal, but there was no evidence of higher temperature mineralization, as if you could remember that little slide I showed you earlier with the temperature stabilities, right? We didn't see quartz alunite kaolinite associations. We did not see anything higher temperature beyond the alunite. And even then, the associations were with kind of like a sintery opal and with jarosite. So, and we found that this alteration was not showing up, progressing with some sort of thermal gradient. And so this is kind of a not a great test well or exploration well no promising, let me put it this way, promising leads. Last one's Lanai. This is the first geothermal well drilled outside the Big Island, which was a huge victory just for the exploration team. And the one thing I want to highlight here really briefly, again, the colors just follow the text. The Lanai was the most promising as it was the most closely related to the other geothermal, which are water-dominated systems in Hawaii. And so these 2 wells are associated with the power plant that's near the Kilauea East Rift Zone. And this is the description of the alteration, where you have basically quartz, calcite, and pyrite in distinct zones past 1 kilometer of drilling. And then you get into chlorite, the same thing with SOH number 4, right? A lot more deeper. And so what that tells us is we're getting the same zonation, even though the temperatures aren't as high, but potentially hitting a reservoir further down, or that this was a past geothermal system that's cooling. But, as I said, geothermal can encompass many different things. And so very promising alteration and logging that we saw here. The next is actually not going to be using in situ methods, rather remote sensing. The reason I bring this up is just because if you're in the preliminary stages of exploration, remote sensing is a great tool. So this is done by Kirk Krall, who's now at ORMAT. But this study he did while he was at Sandia, and essentially he combined hyper and multispectral remote sensing with what we call quaternary faults. So those are young, new fault systems that can help bring elevated heat to the surface, and 2-meter surveys, which is essentially digging a shallow hole into the ground, really tiny hole, and detecting temperature anomalies. And so here is DAC is an already developed geothermal power plant. But essentially the really cool thing about this survey is that it identified in these white letters here areas of where there looked like sinter deposits based on the combination of red and pink pixels, and they promising areas along these quaternary faults. So that means that these fault systems were probably were in the past bringing up hydrothermal fluids, and that maybe if you were a geologist and wanted to focus your study area a little bit more, you might want to focus on these areas that are highlighted in the white. Another case study, rather on the exploration side, is using infrared spectroscopy for a power plant that's already been developed. So again, this is the work from Kirk Krall, and this was actually doing his PhD at the University of Nevada, Reno, using the same spectral evolution instrument I used. And so Geysers geothermal power plant is it's one of the largest power plants in the world, but in the US. And he revisited a well called Prati 40. Again, I want to highlight the high data output and turnaround time here, which is great for, especially for a company that needs data. And essentially what they were able to do using the spectroscopy was map distinct zones of alteration within the well, and sort of match that with the lithological notes, but also with drilling notes about where the steam is being introduced into the reservoir system, and support the model of this sort of vapor-dominated geothermal system. And so here he was able to identify that there are certain alteration minerals that exist in vapor-dominated systems that you may not see in water-dominated systems, such as this sort of acid, steam-heated water intense alteration, sort of like a very higher grade version of a fumarole system, and where the sort of restrictions are in terms of the permeability in the cap rock, where the steam is accumulating, and sort of map that sort of alteration in that reservoir, which is a really great way to do subsurface characterization for geothermal. So I'm coming up on 30 minutes, and so I just wanted to briefly go over those types of case studies, but I'm happy to take any questions. And I also provide my email here, very simple, pooja.sheevam@nmt.edu if you want to ask me a question later. But yeah, happy to take questions now.